Hello, this is part 8 of the Impulse Momentum video series. This will be about center of mass. Center of mass. I'm going to start with point particles. So a set of point particles which are not necessarily connected in any way. And then the second section will be about rigid bodies in 3D, which is just a collection of distribution of very small elements, right? So a distribution of those masses. Okay, a rigid body. So let's start with the general idea of the center of mass. So this could be in 1 dimension, 2 dimensions, or even 3 dimensions. Doesn't matter. All you need is n number of particles. I'm just going to use 2 dimensions on this plane. Let's say there's 1 particle here, another one here at the center, 1 here, 1 there. There's another one here, right there. Okay, these are all point particles. Let's name them M1, M2, M3. Okay, all the way up to M number N. Got many of those. All right, so these are all on the 2-dimensional plane, but this works for 3 dimensions too. So what will be the coordinates? So each particle definitely has a pair of numbers, like this one. I'm going to call it x2 and y2, right? So this one here will have the coordinates xn and yn. It doesn't really matter where you pick your origin. It could be anywhere. And these could be also in motion, right? So let's say this guy is moving here. This one is moving there. No, these could be the air molecules in this room. All right. So the idea is, can we find a point on this plane? Of course, it's a plane. It's not the air molecules. This could be, ants crawling on the paper. Can I find a point that will represent this collection of masses? All right. And that point's movement, in a way, will describe what the group is doing as a whole. Okay, so that's roughly the idea behind the center of mass for point particles. When we do a distribution of mass, it'll be really practical to find where the center of mass is, because if let's say this is my object, this pen, if I just find the center of mass, it'll be balanced around that point. Okay, so practical reason, you're hanging a picture on the wall, you want it to line up perfectly, so you may want to find the center of mass. All right, so let's start with the point particles. I'm just going to give you the definition. So this point right in the middle, let's say somewhere around here, let this be our center of mass. I'm going to put a cross here. Okay, so it's got the coordinates x and y. So this x coordinate of the center of mass will be a fraction. In the numerator, we'll have m1 times x1. And keep adding m2 times x2. Then m3 times x3 all the way up to the last one, mn xn. And then divide this by the total mass. m1 plus m2 plus dot 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 all the way up to mn. Okay. If you prefer a more compact notation, use the sigma summation from I equals 1 to n mi xi over the total mass mi. So m total is this sum I from 1 to n mi. Similarly, the y-coordinate then will be equal to 1 over m total. In the numerator, though, we have each mass multiplied by its y-coordinate. Okay, so that is the definition. If you prefer some vector notation in 3D, let's say, so in n dimensions, although they're not physical, let each particle have this coordinate r. So we're talking about ri. Okay, that's xi, I hat, yi, j hat. I'm just using unit vectors. Zi, k hat. Okay, then the center of mass coordinate is also given by this position vector. Total mass times ri times mi, summation over I. Okay, it's just a formula. So let me give you an example. Let's say on the xy plane, I have, let's say, 3 masses lined up here. One is at the center, one of them is here, and the other one is over here. Okay, these are 2 kilograms, 1 kilogram, and 3 kilograms. Okay, and the distances are 1 meter here, and this is 1.5 meters. Now, if this thing on the right was 2 kilograms, and if this was 1 meters, you don't even need to do any calculation. You would say, okay, in the middle at the origin, you would have a center of mass, but now you expect that center of mass to shift a little to the right. But where exactly? That's the question. So let's mark that point that we are thinking, like right somewhere here. Since they're all lined up on the x-axis, this point cannot have a y-coordinate other than 0. So we know it's going to be on the x-axis, but where is it exactly? Let's say somewhere here. I'm going to mark it as my center of mass. I'm just going to apply this formula for x. X center of mass will be equal to, okay, so the total mass, 1 divided by 2 plus 1 plus 3, 6 kilograms. 6 kilograms. Now in the numerator, I need to multiply the x-coordinate of each mass by the mass. So 2 kilograms on the left. Now this location here is -1. -1 meters. Now the one in the middle is sitting at the origin, which is 0. And then the 3 kilogram mass is at positive 1.5 kilograms. All right, so that's how you find your center of mass. Let's find it. So That's -2 plus 0. -2 plus 4.5, which is 2.5 divided by 6. 2.5 divided by 6, 0.42. That's the x-coordinate. 0.42 meters, right? So what if I shift these masses? Let's say I take my the mass on the right, which is at 1.5 meters. Okay, so I'm going to take that object and move it up a little bit and bring it here. I'm going to leave the one in the middle right there where it is, and then this guy here, I'm going to move it just a little bit this way. This is still 1 meters, and this is 1.5 meters. But this is, let's say, 0.3 meters below the x-axis. And this will be 0.8 meters above. So where is the center of mass now? Okay. Can you make a guess? It's almost like a triangle right now, a triangle formation, right? So let's see, you have this. I mean, my drawing is not to scale, but I'm thinking that's like more like a triangle now. And then, okay, so I guess the center of mass should be somewhere here. That's my guess. All right, so let's put a cross here. Okay, center of mass. But let's find it. The new center of mass, x center of mass, new. And this coordinate, this point, will have a y coordinate as well. It was 0 here, now it's not 0. Y center of mass and x center of mass. Now, if you look at the formula, for the x center of mass, you only have the x coordinates of each particle. And those did not change. I mean, this one is still 1 meter to the left of the origin. This one is still at x equals 1.5 meters. So I don't see any reason why we should have a different x. Okay, so I'm just going to write 0.42 here. 0.42 meters. Let's do the y coordinate. So 1 over the total mass, which is 6 kilograms. Now, the one on the left, 2 kilograms, is at y equals -0.3 meters. And the one in the middle has a 0 y coordinates, I'm ignoring that. And then 3 kilograms times 0.8 meters. Okay, so -0.6 plus 2.4 divided by 6.3. 0.3 meters is the y coordinate of the center of mass. Okay, that's how the center of mass shifts. By shifting those masses, the center of mass itself shifted. Okay, so I mean, you can do as many as you like. Just keep adding. That's what you do. Let's go to the distribution of masses. Let me add one more board here. Okay, let's start with really easy ones, like what if you had like a square? Now, if it is uniform, if the mass is uniformly distributed all over that plate, all you have to do is to use these diagonals and then find the center point. That's the center of mass. I think that's very intuitive, and you can do it for a rectangle too. Just find the geometrical center. That will be the center of mass. What if this plate has a thickness like maybe triangular? The top may look still like a square or a rectangle, but the thickness may vary. Then it's not so uniform, at least in that direction. So it won't be the geometrical center. It'll be closer to this side. So that requires more computation, okay? But for simple objects, let's say you go to Home Depot and buy a piece of, plywood or something, okay? Let's say this is 40 centimeters. And the longer side is 50, not 50, 100 centimeters. Okay, and then you're using this piece of wood for a project, and the project requires that you cut off a corner, or let's say a quarter. This is the middle, so you want to take this piece out. Just cut it. Okay. Now, before you cut it, the center of mass was the center, geometric center. Now we have this L shape, so you expect the center of mass to shift to here. But where is that point exactly? Okay, let's try to find that. It's our problem. Where is our center of mass? All right. So the trick is, well, first of all, we have to place this on our XY plane. So let this be the x-axis, and then you'll need a y-axis. That's not the trick. The trick is the L shape. You can divide that shape into 3 equal parts. So let me use a different color here, red. And for instance, you can take this part here. Okay, this is 1/4 of the original mass. So I'm just going to call it M4. And you have 2 more of these. And these are uniform rectangles, so their center of masses will be at the center. I know that. Now, what if I squeeze all of that mass into one point, which is the center of mass? Like shrink all that mass, same mass, but just occupies a single dot in the middle. So that would be over here, this point there. This is the point mass, which is M/4, and its coordinates are, okay, we're talking about the 1/4 of 100 centimeters, so this will be 25. This is x in centimeters. So this is at 25. Similarly, I have another mass right below it. What is this one? It comes from the mass over here, or the quarter mass over there, this one. So that is now represented by this dot here. Okay, so I take that idea and I do it one more time for the third part here, which is just over here at x equals 75 centimeters. And the y coordinates for these are, okay, divide 40 by 4. So this will be 10, y equals 10 centimeters. Y in centimeters. And then both of them. And this will be 30. Okay, and then you know what to do. These 3 points, point particles, will have a center of mass around somewhere here. Okay, so we got to find the coordinates of this center of mass by using our formula again. So this will have an x coordinate, x center of mass, and it'll have a y coordinate, y center of mass. And the x center of mass will be 1 over total mass, which is 3 m over 4. And now let's go one by one. This one here, that mass is m over 4. Just multiply it by 25. Yeah, one more like this. So right below it, m over 4 times 25. And then the third mass, which is also m over 4. Multiply this by 75. Okay, so the m over 4s cancel. Here I have 75 plus 25, 100, 125. 125 divided by 3. 125 divided by 3, 41.67. 41.67 centimeters. Let's do the same thing for the y. So the y coordinate of the center of mass. Now those masses will cancel, right? So 1 over 3, and I have a 2 at 10, which makes 20, and 1 at 30. So this is 50 divided by 3, 16.67. 0.67 centimeters. Okay, so that's the center of mass of your L-shaped object. Okay, now those tricks may not work every time, okay? These are maybe special cases. What about a formula for a general calculation of the center of mass? Okay, an arbitrary shape. What is the center of mass? It's going to be somewhere here, okay, but where exactly? Now, there's an experimental way actually. You can just hang it from one side. If you do that, if you let it swing freely, it's going to come to an equilibrium, and when it does that, the object, let's say you use this point to tie a string, Okay, so this is the object. When it comes to rest, this is where you're hanging it, right? From the rope. Right below it, you'll find the center of mass somewhere. Okay, you know that for sure. But using the same logic, so just take pen and just draw a line there, and you know it's going to be along that line. Okay, and then try another point. Let's say use this point here to hang the object. I'm going to try to draw it now. So I'm going to have something like this, and then okay, it didn't look exactly like this, but you get the idea, right? And the original line was going through like this, but now you're hanging it over here from that point. Same idea. So the center of mass will be vertically somewhere below it, but you know it can also be on this line. So the only option is where they intersect. Where they intersect. So that's an experimental determination of the center of mass. But let's find it analytically using calculus. Okay, that's the only way. Now, remember the original formula for point particles. This was 1 over mass total, then the summation over each mass and its x coordinate. Now, to do it using integrals, you got to pick a differential mass, a very tiny bit of this object. I'm going to exaggerate. I'm going to make it bigger than it really is. A small cube here. Okay, really small. So if total volume is V, we're talking about the volume, which is dV. Okay, and this dV contains a mass equal to dm. All right. So that's what infinitesimal means. Really small portion of the total mass. So that dm, if I multiply it by x and integrate over the whole volume, it's just like this here. This. All I need to do is to divide it by the total mass, and I'm done. Total mass. I don't even need to call total mass, it's just the mass of the object. Just mass of the object. And the mass of the object then, using the same logic, is nothing but the integral of dm over its volume. Okay, but what is dm? I mean, how do we know how much mass is contained in that infinitesimally small portion of the object? And is the object uniform? Okay, like this mouse has plastic parts and metal parts, so it's not a uniform object. This is probably more uniform, but the shape is really weird shape, right? It's hard to express mathematically, but in general, density, okay? Density is what we need. If the object is uniform, density is simply total mass divided by total volume. Let's use the letter rho to denote density. Now, rho may or may not be a function of where you are on the object. I'm going to call it r, just like the position vector. So if this rho is a constant, it is uniform. If it is constant, this means it is a uniform mass distribution. If it is not a constant, it's coordinate dependent. That's what it means. Or coordinate dependent. Okay, it could be a pen, like an alloy. This part is gold, this part is lead. Okay, all right, so why do we need this? Because dm is rho times dV. That's why. Okay. So for the case of constant or uniform mass distribution, rho is simply total mass, or the mass of the object divided by its volume. If not, we have to know how it depends on the coordinates x, y, z. All right, so that's the density in terms of volume. It's also possible to consider area densities. So if you have a sheet of paper, a very negligible thickness, so all you actually worry about is the area, surface area. So in that case, density would be mass, m, divided by some area. And let's use the letter sigma to denote area density. What about a really long stick? Okay, we can ignore the thickness or the cross-section area. Now we're talking about linear density. And that would be the total mass, or the mass, divided by length. Let's use the letter lambda to denote that. Linear mass density, area mass density, this is the volume mass density. Okay? So let's calculate the center of mass for an object, a linear mass distribution. That's just a pencil, which is really long. Okay, it's like a cylinder, but the cross-sectional area is so small that we can ignore it. All right, so where is the center of mass? And it's a uniform distribution. Where is the center of mass? And it's not difficult to guess, right? It's going to be in the middle. If you just, let's place this in our XY frame. Let the origin be where the left end is, and the right hand side is going to be the other end, along the x-axis. If the length is L, let's say, the length is L, so this is where x equals L. This is x equals 0 on the left side, the y coordinate and the x coordinate. Now, everybody knows that the center of mass will be in the center. That's the uniform object. But let's prove it using this method. So, is it here? Please show, right? So, we'll need an infinitesimal portion of this object, okay? An infinitesimally small part, like a small cylinder right there. This is the smallest part you can imagine on this object, and the thickness is dx. Okay, this dx here, can you see it? I'm going to drop these, just write dx. That's the thickness in this direction. And we're totally ignoring this side, this thickness, okay? We're ignoring it. It's so small. So this much of the object carries a mass, which is dm. So this dm will be the linear mass density, lambda, times dx. Okay, that's the infinitesimal length. All right, so all we have to do is to use the formula above, right there. This will be our formula. So the total mass is, let's say, m, Therefore, lambda is equal to m over L. This times dx is dm. So the center of mass here, x coordinate of the center of mass, will be 1 over m times an integral. The integral will have x, that's in the formula, and you multiply this by dm, which is m over L dx, okay? And the integral will be from 0 to L. 0 to L. Get rid of the m's, and 1 over L is a constant. The integral will be x squared over 2, and you plug in the limits. L squared over L is just L, so L over 2. But you knew that already, right? It's in the middle. Just a simple exercise, the simplest I can think of for the linear mass distribution. How about a surface? Okay, a surface. All right, let's say you go to Home Depot again, you buy a piece of board maybe. Let's say you're gonna make a sign, okay? A sign. You have a shop, you wanna hang a sign here, erect a triangular sign, how about that? But you wanna know where to hang it, so it stays balanced. All right, so that's our problem, finding the center of mass of a triangle. And the thickness of the board is negligible. We're just treating it as a two-dimensional object. Okay, so let's use our XY frames again. This is X, and then you'll need a Y to go with it. And our triangle will be okay, let me use red again. I'm gonna flip the triangle like this. That will make a difference. So I'm just gonna put it here. This is my triangle. Because the goal is to find this point, right, where to hang it. But if you think about it, if you bring it downward, it's a line. So if I say the center of mass here, if I hang it from there, the same result. Okay, it could be any. So I'm going to flip it, and let's give some numbers here. Let's say the height is h, and the base is b. All right, this is the y axis, and this is the x-axis. I want to know where exactly the center of mass is. All right. So for this problem, I'll need a very tiny volume, which will contain a mass dm. That's in my formula, right? dm. So let me pick a small area to work with, dA, and that dA will contain that mass dm. So there are two options here. I could go with a little square, sides dy and dx, or even simpler, I could think of a slab, a very tiny rectangle here. The thickness of this rectangle is dx, but the height is y. So the area here, which I call dA, will be equal to y times dx. I'm thinking of it like a rectangle. In fact, it's a trapezoid, right? But the top part is so tiny, so for a very small dx, infinitesimal dx, that doesn't really matter. So it's like a rectangle. So y times dx will be the area there. And if I multiply that by the density, you know, this sigma here, sigma density, which will be the mass of the triangle, m, divided by the area. Area is 1/2 b times height. So take this rho and multiply it by dA, you'll get dm. So dm will be rho, which is 2m divided by bh times y times dx. And then I integrate this to get the total thing. I'm going to be careful though. There's y here, and y depends on where you are, and it changes with x. So I need y as a function of x. Okay, I have a straight line here, right? So this line is the hypotenuse there. It goes like this from here to there. So I need the equation of that line pretty much. So I could plug that in my integral. So everything will be in terms of x then. So this y has an intercept, which is h. Okay, it's like y equals mx plus b, right? B is the intercept. So I'll need h there, and then the slope will be negative h over b. So y is equal to negative h over b times x, and the intercept is h. Okay, so I have to now find this. X coordinate of the center of mass will be equal to 1 over total mass times an integral, which is x times dm. So dm has 2m over bh, that's dm, times y, which is negative h over bx plus h, times x times dx. Okay, and the integral will be from 0 to b. Now check what happens to h. It goes away, okay? So the answer will be not depending on the height of the triangle, and m will cancel too. So there's no m there. That's what you'd expect anyways. So let's factor this 2 over b out. 2 over b times from 0 to b, the integral of negative h over bx squared plus x dx. All right, so we're getting there. 2 over b. Now the lower limit will not give you anything, it's 0. Here we have negative h over b. Now this will be x cubed over 3, so b to the power 3 over 3 plus b squared over 2. Okay, so one of the b's over here will go away, and this will take care of the other one, and this will go away, so there will be only b left. I thought we got rid of h. Yeah, I don't know why I carried that h there. Let me just erase it. This h goes away. See, it cancels. Just gonna write 1 there. Just 1. So I have 1/2 minus 1/3. So that is 1/6. And then 1/6. Okay, this is 1/6. There's a 2 in the numerator. The answer is 1/3 of B. That's where your center of mass is. 1/3 of the base, closer to the edge, that way. Okay, I'm gonna stop it here and maybe solve one more example in the next video.